Hey everybody, I had a question or two on projectiles, so I decided to just go ahead and make a quick video review of projectile motion because I'm that anxious to help you guys out. So anyway, I'm just going to flip my screen here. Okay, so first of all, for projectiles, there's two types. We have horizontal. A horizontal projectile means it only has a velocity in the horizontal direction to start with, and then it's going to follow that parabolic path. And then we have angled projectiles. So angled projectiles, you could be on a flat surface and it's launched like that and it goes like that. You could be up a height, launch it up at an angle like that, or you could be up at a height and launch it down at an angle and do something like that. Kind of bad pictures, but I think you get the idea. Okay, so first let's talk about horizontal. Okay, so for a horizontal projectile, you have to have a height to start out with. If you didn't have a height, you just launched a horizontal projectile from ground level, it would just roll. It wouldn't be a projectile. So you have to have a height. Okay. So something like this. Now, the time it's in the air is only going to depend on the height, and that's it. Okay, because gravity is what's pulling the object down. Gravity is what's going to dictate the time. So you only look in the y direction to figure out time for really any projectile. So back to when we talked about projectiles, we did the analogy like a bullet. You drop a bullet from the same height, you fire a bullet horizontally. Which one hits the ground first? They hit at the same time because they're both falling the same height. They're both under that same gravitational field, 9.8 newtons per kilogram, or the acceleration 9.8 meters per second. They're going to be in the air for the same amount of time. Doesn't matter how fast it's moving horizontally, it only matters how far it's moving vertically. Okay, so if you have different heights, like you've got one here, it's got some velocity in the x direction versus this, which has the same velocity in the x direction. This one has a bigger height, so it will take more time to hit the ground than this one. Okay, now I'll just call this T1, T2. So we can say T1 is greater than T2. If we look at range, in other words, the horizontal distance it travels before it hits, that is all in the, well, it is the x direction. If you remember, there's no acceleration in the x direction, so really the only equation we're ever going to use in the x direction is v equals delta x over t, and that's true for any projectile. But right now we're talking about horizontal. So if we look at the range, delta x is that horizontal velocity times time. So in these two cases, if they have the same horizontal velocity, whichever one has a bigger time is going to go farther. Okay, so that's the range. Now, be careful. If the velocities are different and the heights are different, you really have to use some calculations to know which one's going to go farther. The one at a shorter height will always have the smaller time, okay, as long as it's horizontal. But in terms of which one goes farther, if you have a different time, meaning a different height, and velocity is different, you really have to kind of calculate that out to see the difference there. Okay, so that is horizontal projectile motion. All right, with angled projectile motion. Okay, so let's look at a case first. We're up a height like this. Okay, and let's have a situation like that. Now, same height, but a much lower angle. Okay, which one will be in the air for a longer period of time? Again, that depends only on the y direction, the vertical direction. So if we were to componentize this one, Okay, you see this has a bigger component of velocity in the y direction, and this has a smaller component. So it's just like you throw two balls up in the air. One you throw at a very high speed, one you throw at a very low speed. Well, the one you throw with a higher speed is going to go higher. It's going to be in the air for a longer period of time, which is the case right here. So if I call this T1 and T2, so in this case T1 will be greater than T2. Okay, now notice when you change the angle, you're also changing the horizontal component of the velocity. So which one goes farther? Well, that's going to be a little more difficult to answer. You're going to probably have to go in and do some calculations there. Okay. I made a couple notes here. I want to make sure I'm covering things. Okay, we can even look at a case where we throw it down at an angle. Okay, and again, same height, but a shallower angle. Okay, so again, if we componentize, okay, time depends only on the vertical component. So if I call this T3 and T4, well, which one's going to hit the ground first? In this case, since we're throwing them down, this is going to hit the ground first. Okay, it's like if you throw a ball straight down and just drop it. Okay, this one will take less time. So here I'm going to say T3 is less than T4. Okay, again, for the range, you really have to take more into account. Okay, so because that's going to depend on the velocity in the x direction as well as time. Okay, now for the lab, we launch things off the flat ground. Okay, so something like this versus something like this versus something like, let's say, that. Okay, and let's say they're all launched on the ground, land on the ground. Which one will spend the most time in the air? Well, it's going to be the one with the biggest vertical component of velocity. So if I call this T1, T2, T3, I know T2 is going to be the biggest, and then T1, it's got the next biggest vertical component of velocity, and then T3 is finally going to be the smallest one. Okay? All right, so let me go to the lab real quick. All right, the PhET simulation. Okay, so in the PhET simulation, just by default, this is at 80 degrees. Let me take the speed down a little bit. Let's go 10 meters per second. Okay, we're going to launch this. Okay, so it doesn't get very high, it doesn't go very far. Now we're going to have the same angle, 80 degrees, and let's double the speed. Okay, so this one took right about 2 seconds. Okay, now we're doubling the speed. What's that going to do to the time? Well, if you look at the y component, okay, the y component will be 20 times the sine of 80 degrees versus the previous one, it was 10 times sine of 80 degrees. So our y velocity is doubling. We should see double the time, right? Or is it one of those trick ones where it's like 4 times or something like that? Let's check it out. Hey, hit the target. Okay. 4 seconds. Okay. So it is double the time. All right. And if you think about acceleration due to gravity, let's just say 10 meters per second. You throw a ball straight up at 10 meters per second. Gravity is going to slow it down by 10 meters per second every second. So if it leaves your hand at 10 meters per second, after 1 second, well, it loses 10 meters per second at 0. And then it comes back down. It's going to take 1 more second to come back down. All right. That's kind of what we saw in that first situation, so 2 seconds. Now let's double that to 20 meters per second. You throw a ball straight up at 20 meters per second, it's going to lose 10 meters per second every second. So it's going to take 2 seconds to go all the way up, 2 seconds to come back down, so 4 seconds total. Okay, I think we're seeing that with this example because this is such a steep angle, it's very nearly vertical. Okay. All right, now one other thing I want to do is let's look at an angle. Let's just do like 65 degrees. Okay, and let's settle down on the speed. Let's go 15 meters per second. Okay, and let's launch this. Okay. All right, so again, the y component of velocity dictates how much time it's going to spend in the air. The x component gets it across. Okay, so they work together to get the overall range of this. All right, so let's look at this. Let's get a range on it. It went 17.57 meters. Okay, now again, this has a fairly big vertical component for velocity, a smaller component for velocity in the horizontal direction. Now I'm going to lower this to 25 degrees. Okay, and I'm going to launch it again. All right, so now I should have less time in the air. How much time was this, by the way? Okay, so 2.77 seconds. So I should have less time in the air, but I have a bigger horizontal velocity. So how is that going to balance out? Let's launch it. Boom, whoa, same spot. Wow. Okay, so it hits at the same spot, yet it has less time in the air. Okay, so that's a feature about projectile motion is if you launch it and land it from the same level, in other words, ground level to ground level, complementary angles will give you the same range. So that's how the first one was 65 degrees. That's how I knew to go to 25 degrees on the second one to get that same range. Okay. That does not work if you're changing elevations though. So if you're on a cliff and you do this, the complementary angles would not give you the same range. There's more things going on in that. Okay, so I hope this was a decent review for projectile motion. I hope I answered any questions you have. But please, if you have any further questions on projectiles, let me know. I'll address them. Or, if you have any questions on anything else. One thing I didn't mention is, we could change the mass of this. We should know by now that mass is not going to affect anything. We could change the mass. We're going to see the same results on that. Okay. All right. That's it for now. Thanks for watching if you made it this far, and we'll talk to you later.